Functional groups are the reactive part of the molecule. There is a variety of functional groups. We will list them all, and you will learn how to draw them and identify them. Starting with hydrocarbons. Hydrocarbons are classified into alkanes, molecular formula CnH2n plus 2, alkenes, and alkynes, which is CnH2n negative 2. We know that the DBE of alkanes is 0. For alkenes, the DBE is 1, depending on how many double bonds you have, because every double bond is a DBE of 1. And then for alkynes, every triple bond is a DBE of 2. So it depends how many double bonds and the triple bonds you have. So alkenes have no functional group. They are just long carbon chain. When we have more than one carbon, we prefer to draw the alkane chain in a form of a skeleton rather than in a form of structural formula. Make sure when you draw the alkane just to draw them as a zigzag representation to keep the tetrahedral geometry of every single carbon. A long carbon chain normally is abbreviated by an R. So you're going to see whenever we start talking about organic molecules in there, we're going to use the abbreviation R. R is an actual chain. It's a long carbon chain. And that carbon chain can be one carbon, two carbons, three carbons. So it's the general representation of alkanes. Alkanes have no functional group. Alkenes, on the other end, they have a double bond functional group. So um, when you want to identify the functional group of alkene, just go ahead and highlight the double bond part. Now, the double bond can be either at the end, it can be in the middle, it can be in a cyclic structure. Whether in any of those forms, you just circle or highlight the double bond, and this is called an alkene functional group. This means that the reaction is going to start from there. If the double bond is in the middle, then this is going to be an internal alkene. And if it is at the end means that the ending of the alkene is actually a CH2. Okay, still every carbon of the alkene is going to be an sp2 hybridization. So whenever you have a double bond, every carbon of those is an sp2 hybridization. This is a trigonal planar geometry. Now, with respect to alkynes, alkynes have a triple bond functional group. Highlight the triple bond. Whether the triple bond is at the end or in the middle, we're going to give it a name terminal alkyne or internal alkyne. Now, when you are assigning those in the problem sets, you don't have to use the terms terminal and internal. Just go ahead and write it as a general alkyne. But remember that alkynes are going to be linear geometry. So if they are linear geometry, their hybridization is going to be an sp hybridization for each of the carbons that are connected to the triple bond. However, the carbon that is adjacent to the triple bond, so here I have one carbon adjacent, here I have two carbons adjacent. So these carbons that are adjacent, they have to be linear as well, with a bond angle of 180 degrees. So the bond angle here is going to be 180. The bond angle here is going to be 180. So you have to write it as a straight line. Now with terminal alkynes, we have at the end the sp carbon that has an sp hydrogen, sp3. This is an acidic hydrogen in there, so if there is any very strong base, the base will come and take this hydrogen and you will have an acid-base reaction. Benzenes are another type of hydrocarbons. The molecular formula for the benzene is C6H6. Benzene is a cyclic compound. Benzene's double bond equivalence, because it is a cycle, every cycle is a 1 dBe, and every double bond is 1 dBe. So it's a cycle in 3 double bonds, so its dBe is equal to 4. When we represent benzene, we can represent it in any way of its resonance forms, or the best way is to go ahead and represent it in its hybrid. Just put a circle in the middle. When we name benzenes, there's a couple of names for benzenes. Benzenes can be named as phenyl groups. We abbreviate the phenyl by PH, or we can name them as arenes. And arenes are aromatic hydrocarbons. Okay, um, the AR for the arenes stands for the aromatic. So benzenes again, if they are part of the chain, so this is your main chain in there, and benzene is a branching off the chain. Sometimes we like to abbreviate that benzene, so we write a PH. Phenyl is exactly the same as benzene. Whenever you want to name benzene, you can use either the name benzene or phenyl or arene. All of those are going to be the same. This is an example in there. So you're going to have like a big molecule and you're going to be asked to assign the functional groups. All what you need to do is just circle those functional groups and name them. As I said, you don't have to name the alkynes and alkenes as terminal or internal. Just go ahead and name them as is, alkenes or alkynes. Alkyl halides are another type of functional group. The general formula is Rx. R is a long carbon chain. X is any of these halogens. Whenever you want to name, the ending is going to be in the halogen and put an ID at the end. So it's going to be an alkyl fluoride, alkyl chloride, and so on. Halogens, since they are the reactive part of the molecule, you need to show all the lone pairs because they are heteroatoms. So make sure that the lone pairs are shown. And when you want to highlight the alkyl halide, you highlight the carbon that is connected to the halogen together with the halogen. So this is called an alkyl chloride. Okay, so you highlight the carbon together with the halogen. Don't highlight just the halogen. No, it's the carbon that is connected to the halogen. Now, the classification of alkyl halides. Alkyl halides are classified based on how many carbons they are connected to. So for the first example here, this alkyl halide, so again, when I say an alkyl, I mean a carbon connected to a chlorine. So this alkyl halide is connected to one carbon. So if it's connected to one carbon, I'm going to call this a primary alkyl halide. If the alkyl halide is connected to two carbons, then I'm going to call this a secondary alkyl halide. And if it is connected to three carbons, this is one, this is two, and this is a three, we're going to call this a tertiary alkyl halide. Tertiary means a three. We can abbreviate the tertiary as either a T or TRT, or we can write the name as a whole tertiary in there. The bond between the carbon and the halogen in the alkyl halide is a polar covalent bond. So this bond here is a polar covalent bond. And this bond here generates, of course, because it's polar, so it generates a dipole. It generates a direction of polarization since the chlorine is more electronegative than the carbon. The hybridization of this carbon is an sp3 hybridization. So you have a carbon sp3 connected to the chlorine. So the chlorine is going to be more electronegative than the carbon. So the pull of electrons is going to be towards the chlorine. When you have a motion of electrons, you're going to generate a dipole. A dipole is basically the movement of electrons that shows which site in the molecule becomes electron rich and which site in the molecule becomes electron poor. So in this case, this carbon is going to lose its electrons to the chlorine. So it's going to be electron poor. This electron poor, we're going to represent it as E plus. Another name for it is the electrophile. So E plus is going to stand for electrophile. Okay, and we represent that by a partial positive. So you have a partial positive sign and a partial negative sign. This is the only bond in the whole structure that is a polar covalent bond. All the bonds between the carbons, the CC bonds, these are non-polar covalent bonds in there, which makes alkyl halides completely water insoluble. Another type of functional groups are functional groups that contain an oxygen and a nitrogen. So let's start with the ones that have oxygens in there. These are alcohols. Alcohols, they have no double bonds. So whenever you have an oxygen in your molecular formula and your DBE is zero, think that your structure might be an alcohol. So this one has a DBE equal to zero in case there is no double bonds, there is no alkene in the structure. It's just like pure alcohol there. So alcohols are classified into, again, primary alcohols, secondary, and tertiary alcohols. And to classify the alcohols every single time, you highlight the carbon that is connected to the OH together with the OH. So the carbon that is connected to the OH together with the OH, and see how many carbons it is connected to. So this one is connected to two carbons. This is connected to one carbon, so it's called primary. This one is secondary, and this one is going to be a tertiary alcohol. Whenever you want to condense alcohols, since the OH belongs to the carbon, then if it is terminal, you can put it in the name without any parentheses. However, if it is within the chain, then because OH is a polyatom, and normally we do this with polyatoms, you always need to put it in parentheses. So this means that the OH belongs to the carbon before it, so it belongs to the CH. Ethers have a general formula of ROR. The oxygen is between two carbons. And the R's can either be the same, that will result with a symmetrical ether, or they can be different, and this is going to be an unsymmetrical ether. Ethers are not classified. So with ethers, I don't have primary, secondary, and tertiary. These are examples of symmetrical ethers and examples of unsymmetrical ethers. You can easily see the R's on opposite sides of the oxygen. These are different, together with their condensed form. When you want to condense ethers, you condense the R's if they are the same and put the oxygen at the end. If they are not the same, then the oxygen is going to be between both R's. If you're looking at ether again, and if you want to draw the direction of polarization for ether, oxygen is way more electronegative than the carbon. This means that this is going to be partial positive, and this carbon over here is going to be partial positive as well, and the oxygen is going to be partial negative. Ethers can be involved in a cycle. If this is the case, then the double bond equivalence, since it is a cyclic ether, it's going to be 1. The simplest type of ether is an ether that is involved in a three-membered ring. We call this ethylene oxide. Ethyl is two carbons, and here I have carbon 1 and carbon 2. And this is a three-membered cycle because there are three elements in the cycle. This is the simplest form of cyclic ethers. We have ethers that have four-membered rings, ethers that have five-membered rings, and ethers that are in a six-membered rings. With respect to epoxides, epoxides are very reactive. And the reason they are reactive because they have very weak sigma bonds. The sigma bonds are between the sp3 hybrid carbon and the oxygen. Now we know that since we have carbons that are sp3 hybridization, we know that the bond angle for the sp3 is around 109.5. So the bond angle is around 109.5. This is the ideal bond angle for a tetrahedral structure. However, in reality, the bond angle for the epoxide is just 60 degrees. So notice how the bonds are squished from the 109, they are compressed actually, from the 109.5 to 60 degrees. This is because there's a lot of angle strain in the epoxide, which makes these two bonds here very weak sigma bonds. And because they are very weak sigma bonds, they can be broken easily. So this is why we say that this is the reactive site of the molecule. Epoxides, they also have direction of polarization. We are looking at a polar bond between the carbon and the oxygen. So the direction of polarization is actually between the carbon, the sp3 hybrid carbon, and the oxygen for both bonds in there. That is going to generate an electrophilic carbons on either ends in there. So both of these carbons will be partial positive. These will be the electrophiles. So in case you have any nucleophile in the reaction, then the nucleophile is going to come and attack either one of those carbons based or depending on how substituted it is. We will be working with these reactions in organic one, so we will explain those in details. But the idea is that the nucleophile normally attacks one of these partial positive carbons, not both of them at the same time. It's just one of them. So let's say, for example, if the nucleophile came and attacked this partial positive carbon every time you make a bond, because you will be making a bond between the nucleophile and the carbon, right? So every time you make a bond, you are going to break a bond. So we are expecting that the bond between this carbon and the oxygen to be broken. So you have to show that the electrons of this bond are going to go towards the oxygen, and the oxygen will be still connected to the adjacent carbon. So now the oxygen will be a negative charge, but the result is the addition of the nucleophile on the electrophilic carbon. Whenever epoxide is present in a molecule and you want to locate the functional group, please highlight all the epoxide, the oxygen together with its carbons, and that is going to be the epoxide functional group. Okay? Amines. Amines are another form of functional groups, and amines, they do now contain nitrogen. So if you have a nitrogen in your molecular formula and you do the DBE, and the DBE ends up to be a 0, then in this case, your functional group is going to be an amine. Amines are classified again into primary, secondary, and tertiary. And amines are derived from ammonia. So ammonia is a trigonal pyramidal with an sp3 hybridization on the nitrogen. And those lone pairs, they belong to the sp3 hybrid orbital. If you substitute any of those hydrogens in there, then you're going to end up getting either primary, secondary, or tertiary amine, depending on the degree of substitution. So if you substitute one hydrogen with a carbon, then in this case, you're going to end up getting primary amine. So primary amine ends in two H's, so it's an NH2, and it is terminal. The NH2 is terminal, and the nitrogen is connected to one carbon. Now notice here when I am circling or highlighting my functional amino group, you don't have to highlight the carbon with it like the OH. Normally we just highlight the nitrogen, just the nitrogen in there. You can also highlight the two hydrogens, it is fine, but you don't have to highlight the carbon. So this nitrogen is going to be a primary because it is connected to one carbon. This nitrogen here is going to be a secondary because it is connected to two carbons in there. This is another example of a secondary amine as well. Moving with the functional groups, we have functional groups containing carbon double bond O. Now, carbon double bond O is called carbonyl. Carbon double bond O, this is called carbonyls. And carbonyls come in different forms. The first form is whenever the carbonyl has a hydrogen next to it and it is connected to a carbon chain. So it should have a carbon chain and a hydrogen. This is called an aldehyde. The aldehyde part is the carbonyl, not just the carbonyl. So when you have an aldehyde, you highlight the carbonyl and you highlight the hydrogen with it. The hydrogen is a must to highlight. Now, if you have your aldehyde in a skeletal form, then you don't need to show the hydrogen, so just highlight the carbonyl. The condensed form is when because we want to differentiate between this and the alcohol. So whenever you want to condense a carbonyl with the aldehyde, you write it as a CHO. Please don't write it as a COH because a COH is an alcohol and OH is an alcohol. So we want to differentiate between an alcohol and an aldehyde. So you have to write it as a C. This is how I read it: a C, an H, and an O. So whenever I see a CHO, this is immediately going to be an aldehyde. Aldehydes normally they occur at the end. So they are always terminal because of the hydrogen. Okay. Ketones, on the other end, they still share a carbonyl. However, instead of the hydrogen, you have another R chain on the other end or on the other side of the carbonyl. So you have two R chains on both sides of the carbonyls. The R's can be same or they can be different. It really depends. Whenever you want to condense the CO here, you just condense it as a C and an O. If you have similar R's, then combine the R's and then do the CO at the end. If the R's are different, then put the CO in between both R's. In general, carbonyls, they have a direction of polarization because of the electronegativity of the oxygen. So for carbonyls in there, whether it's an aldehyde or a ketone or any structure that has a carbonyl, the oxygen is more electronegative than carbon. So this is going to be the direction of polarization. Pull of electrons is going to be towards the oxygen, making the oxygen fully charged and making the carbon an electrophile. So the carbon is going to be an electrophile. This means that if you have a nucleophile in the solution, then the nucleophile is going to come and attack the carbon. If you have an electrophile in the solution, then the lone pairs of the oxygen are going to come and attack the electrophile. Notice how my arrows start. The arrows always start from the source of electrons. So if you have a source of electron in solution, that source of electron will come and attack the electron deficient site, which is the carbon of the carbonyl. And if you have an electron deficient reactant, let's say for example, then in this case, the oxygen of the carbonyl will come and donate its electrons. Carboxylic acids are another form of carbonyls. And whenever you want to highlight the carboxylic acid, you highlight the carbonyl together with the OH. So this whole thing is called carboxylic acid. These are acids, and these are very acidic with a low pKa. So if I am comparing the acidity of a carboxylic acid with that of an alcohol, definitely the carboxylic acid is going to be way more acidic. The difference between carboxylic acids, ketones, and aldehydes is basically the group that is connected to the carbonyl on the right. So here I do have a hydrogen. Here I do have an R, and the carboxylic acid here I have an OH. Highlight everything, and this is going to be a carboxylic acid functional group. We condense it as a CO2H or a COOH in there. Any one of those can work, and this is how we write it in a condensed formula. Carboxylic acids are like aldehydes, they are always terminal, meaning that they are always at the end. Another functional group is the ester. The ester bond is the CO bond, and the ester group is the carbonyl connected to the oxygen. So this whole thing is the ester group, and the ester bond is the CO bond. The ester bond is a very reactive bond. This is a weak bond between a carbon, sp2 carbon, and the electronegative oxygen. So this is the sp2 carbon and the electronegative oxygen in there. And this bond can be broken easily. So this is the reactive part of the molecule. Esters are carbonyls connected to an oxygen. So whenever you have an example in there, or whenever you have a molecule that has an ester group, please highlight both. Don't highlight the oxygen alone and say this is an ether, and the carbonyl alone and say this is a ketone. No, because you have an ester bond. So if you have a carbonyl next to the oxygen, please highlight both of those, and this is an ester group. Esters can be either in a chain or they can be in a cycle. And if they are a cycle, then this is going to be called a cyclic ester. And just highlight the ester part, and this is going to be your ester group. Another type of functional groups are anhydrides. Anhydrides are made up of two carbonyls connected by an oxygen. You cannot separate them. So whenever you have an anhydride, please highlight it all. This is not two ketones and an ether. This is an anhydride functional group. To condense the anhydride, it depends on whether you have symmetrical or unsymmetrical anhydrides. If you have a symmetrical anhydrides, then go ahead and combine the R's. So here I have 3 carbons on this side. I have 3 carbons on the other. So this is why I can simply condense them, okay, by 2. And I have 2 carbonyls, so I can include that in the parentheses as well. And then these are connected by an oxygen. You go ahead and you put the oxygen. If you have an unsymmetrical anhydride, then you would need to start with the longer carbon chain. So this is a CH3. You have a CH2 in there. Okay, this is your CH3. This is the CH2. It's exactly as you read it. You have a C and you have 2 O's. This is an O and this is another O. So you have the C and the 2 O's. And then you have the carbonyl, which is the CO. So you write it down. And then at the end, you have your CH3 in there. Amides are another functional group that contains a carbonyl. And like the ester, you have an amide bond. And the amide bond is between the carbon and the nitrogen. And this is a weak bond that can be broken, okay, in reactions. So the amide group, the amide functional group is the carbonyl and the nitrogen. And next to the nitrogen, you can have, like amines, you can have either hydrogens or you can have R's. You can replace the hydrogens with the R's. We have different types of amides. We have a primary, we have a secondary, and we have a tertiary amide. So with the primary amide, your amide group is connected to a carbon. So the nitrogen over here is connected to one carbon. So if it's connected to one carbon, see, this is the amide bond in there. So you have your nitrogen, and this bond is the amide bond. So if this nitrogen is connected to one carbon, because on the other side it's connected to no carbons, it's 2 hydrogens here, then we're going to call this primary amide. Primary amide ends up in NH2, but next to the nitrogen you immediately have a carbonyl. This is what differentiates it from an amine. Remember that an amine is this. So this is a primary amine. This is the difference between both. A primary amine is an amine which is connected to one carbon. So you still have your NH2 in there, but the nitrogen is connected to one carbon. If this carbon is a carbonyl, then it is going to be a primary amide. Secondary amide is whenever the nitrogen is connected to two carbons. Okay. And tertiary amides whenever the nitrogen is connected to three carbons in there. So the carbonyl is a must for us to name it as an amide. When we condense the CO, the carbonyl is condensed as a CO. And next to the CO, immediately there is a nitrogen, so please write it down. And then it depends how many R's you have. Here I do have a CH2, CH3. Just write it in the parentheses. Now these parentheses, they are optional though. You can take them out. You don't have to put them in. However, we prefer to put them in, especially if we are working with a tertiary amides, because with tertiary amides, you have two R's on the nitrogen. So it's easy whenever you look at them and whenever you want to write down the structure, you would know that these carbons in there, they do belong both to the nitrogen. So you know that this nitrogen is connected to a carbonyl. This is one, and then this is a group, and this is another. So it's the three carbons in there. So this is a tertiary amide. Nitriles are another example of functional groups. They are carbon triple bond nitrogen. Since it's a triple bond, then the double bond equivalence is equal to 2. The nitrogen is more electronegative than the sp carbon. So there is a direction of polarization creating a dipole, and this carbon is going to be the electrophile. When you condense nitriles, nitriles is condensed in the form of a CN. When you show it in the skeletal form, please make sure to label the lone pairs on the nitrogen. Lone pairs on the nitrogen. Another example of carbonyls is acid halide. It's called an acid because it's a derivative of carboxylic acids. Instead of the OH, you have a halogen, and the halogen can be either a chlorine or a bromine, so you can name it either an acid chloride or an acid bromide. You can name it either an acid or an acyl. It's both the same. When you highlight the acid chloride or the acid bromide, you highlight the carbonyl together with the halogen. And when you condense, it's a CO connected to the chlorine. Let's have an example. We're going to assign the functional groups and label them. So we're going to start with the alkyl bromide. The alkyl bromide is connected to carbon 2 and 3, so this is why it is a tertiary. Be specific, don't say alkyl halide because you already know what is the halogen. So this is an alkyl bromide. This is an arene or a benzene or a phenyl, any one of those. This is going to be the ether. This is an amide. And you got to classify the amide. What type of amide is that? Because the amide is connected to two carbons. You have your nitrogen in here, and the nitrogen is connected to two carbons. So this is going to be a secondary amide. You have your alkene. Alcohol, circle the carbon together with the oxygen. And this alcohol is connected to two carbons, so it's going to be a secondary alcohol. This here is going to be a cyclic ether. It is not an epoxide. Epoxide is whenever you have a three-membered ring, an oxygen and two carbons. This is an epoxide. But this here is more than that, so this is going to be called a cyclic ether. Oxygen here is connected to the carbonyl, so I have to circle both, and this is an ester. This is a ketone. There is nothing on both sides. There is no oxygen or anything on both sides, so this is a ketone. And because the carbonyl here is at the end, this is an aldehyde. Aldehydes always occur at the end. So you have here the ester. This is not an anhydride because the carbon there is a carbon between the two carbonyls. This is not an oxygen, so I cannot say that this is an anhydride. This is going to be a ketone. This is going to be a tertiary alcohol, a cyanide. You could have circled the carbon if you want with the CN. And if you circle the carbon, this is going to be now an alkyl cyanide. Now I have here the carbonyl connected to an oxygen and then another carbonyl. I cannot separate those, so I have to circle all of those. And this is an anhydride. So you cannot say that this is an ester and this is a ketone. You cannot separate. Or you cannot say this is a ketone, this is a ketone, and this is an oxygen. Also, you cannot separate. This is going to be an alkyl halide or an alkyl chloride to be specific. And that alkyl chloride is connected to a carbon and two carbons, so it is a secondary. This is an alkyne, and this is an acid chloride. My primary amine. Primary because the nitrogen is connected to one carbon. This is why. And then I have my primary alcohols. I have my tertiary alkyl chloride. This is going to be my secondary amine. It's secondary because the nitrogen is connected to two carbons. And then I have my secondary alcohol. These two are secondary alcohols as well. And this one is going to be a tertiary amine. I think I still have one more over here. And this is the different types of amides. So this one, since it ends in NH2, it's a primary amide. And it's a primary amide because the nitrogen here is connected to a carbon. Here the nitrogen is connected to two carbons, so you circle the nitrogen together with the carbonyl is a must, and this is going to be a secondary amide. And here the nitrogen is connected to three carbons, so again you circle the nitrogen with the carbonyl, and this is a tertiary amide. As we did for alcohols, alkyl halides, and amines and amides, we're going to do exactly the same thing for carbons and alkanes. So we're going to classify them based on how many carbons they are connected to. So if a carbon is connected to one carbon, then we're going to call this a primary carbon. And its hydrogens are going to be primary hydrogens. So all of these hydrogens are primary hydrogens. So a primary carbon has three hydrogens because it is connected to one carbon. And carbon makes four bonds. A secondary carbon is connected to two carbons, so this means that it has two secondary hydrogens. And a tertiary carbon is connected to three carbons. This means that it has one tertiary hydrogen. So we're classifying the hydrogens and the carbons. So this is a tertiary carbon, and this hydrogen is a tertiary hydrogen. So it's a tertiary hydrogen because it belongs to a tertiary carbon. This is a secondary hydrogen or secondary hydrogens because they belong to a secondary carbon. Quaternary carbon has four carbons around it and has no hydrogens.